So these are our notes for Unit 7. The goal of this unit is going to relate to hypothesis testing. Okay, so this unit will cover hypothesis testing for both means and proportions. Students will need to distinguish when scenarios are presented as either a mean or a proportion and adjust their techniques accordingly. So this is similar to stuff we've done pretty much all semester, but really got heavily into when we got into confidence intervals. We'll look at the two primary errors, which kind of motivate how we set up our hypothesis techniques, specifically type 1 alpha and type 2 beta errors. And then we'll make conclusions based on determined p-values from the execution of those said tests. Okay, so our introduction here. A significance test, or a hypothesis test, is a formal procedure for comparing observed data with a claim, also known as a hypothesis. So similar to how we looked at those claims with our confidence intervals, whose truth we want to assess. The claim is a statement about a parameter, so dealing with something from the population, whether it be a proportion or a mean. And we express the results of a significance test in terms of a probability that measures how well the data and that claim agree with one another. We did our confidence intervals. We talked about them as an exploratory process. So it's something as a statistician we would do ahead of time to get a feel for our data, to kind of see, hey, what is it saying and what might it lead me to? Should I investigate further? Do I need to look more at my sample? This is the point where we can actually go ahead and say, okay, something is or is not different from that claim. So it gives us a little more power in our analysis of data. Okay, let's start things off. What is alpha? Well, here, alpha, pronounced as and spelled alpha, is what is known as a level of significance. So the typical ones we'll see here are going to be 1%, 5%, and 10%, often represented as the decimals 0.01, 0.05, and 0.10. Alpha is the probability of making a type 1 error. And we'll get more into that later. Just kind of like vocab type stuff. The relationship between the hypothesis or significance testing and confidence intervals is that the confidence level percentage and alpha always add up to 100%. Such as a 95% confidence interval corresponds to alpha being 5%. So they go together. These are basically two ways of looking at something in the same method. So again, it's kind of, we use them in that exact relationship there where they add up to 100. Again, stating hypotheses. These are often given to us in words and we translate them into symbols. So a significance test starts with a careful statement of the claims we want to compare. The first claim is called the null hypothesis. So it's the assumption, it's what we're going in to test against. Usually a null hypothesis statement of no difference. So that's what we're always going to say. So it's going to be equal to some number. The claim we hope or suspect to be true instead of that null hypothesis is called the alternative hypothesis. So we have two things that start off every single hypothesis. We have an H sub 0, our null hypothesis, and an H sub A, the alternate hypothesis. Sometimes you'll see that label as H sub 1. I always use H sub A just to keep the word alternative in mind. So for our definition, the claim tested by a statistical test is called the null hypothesis. The test is designed to assess the strength of evidence against it. Often the null hypothesis is a statement of no difference. And again, we're using that alternate hypothesis of what we think the data says is true. Okay, so looking at these hypotheses, our null hypothesis is literally always going to look like this. So H sub 0, colon. Parameters, so if we're using means, it would be mu. If we're using proportions, it would be p. And it's equal to whatever value we're given in that problem. For the alternate hypothesis, we have three different possible things. We have a less than. So notice the value is the same. It always is going to be that same number. So we could look at it's less than, we could look at it's greater than, or simply just different, so not equal to. And again, to determine the correct setup for this, because the parameter is the same. So if it's p, they're all p. If it's mu, they're all mu. Value, we're told the value in the problem. It's 50, if it's 0.2, whatever it may be, these are all the same. All that changes is which one of these we're using. So it's a one-sided if we're looking for strictly greater or less than. Two-sided is that not equal to one. That goes more into like the sketching of the area of rejection and stuff. Essentially, our key idea is we just want to get really good at writing these. So our three possible ones here. A less than hypothesis In this scenario, we are testing the claim that the actual parameter is lower than we previously thought. So maybe we get a sample mean that's lower, we want to test it to see if it's significant. A greater than, same thing, we're seeing if it's actually higher than previously thought. In the not equal to, it's just basically saying it's different. So we're looking to say, okay, can we say it's different from what we thought? Okay. Interpreting p-values. So the p-value is like the outcome of our test here. So what we want to look at, the null hypothesis states that the claim we are seeking evidence against, the probability that measures the strength of the evidence against a null hypothesis is called a p-value. So the definition, the probability computed, assuming the null is true, that the statistic would take a value as extreme or is more extreme than one actually observed is called the p-value of the test. The smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. So a p-value is like golf. The lower the score, the better. It's a probability, so we know we're bounded between 0 and 1. So again, the smaller, closer to 0, the stronger it is. And there's some alternate interpretations here. Okay, so making conclusions. There are exactly 2 conclusions we can make. If the p-value is less than alpha, we reject the null hypothesis. And this is different in a variety, depending on the textbook you're using, the teacher you have. Some use less than or equal to. I always prefer the strictly less than because that way we know rounding is not an issue, right? And then, so again, if the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than or equal to alpha, so not less than, we fail to reject the null hypothesis. So the key idea here is that we are doing one of 2 things and only one of 2 things with the hypothesis set. We either reject the null hypothesis or we fail to reject it. That's it. We never accept the null hypothesis. So we're never going to say it's true. We either reject it or we fail to reject it. Okay, now we got to talk about errors. So a type 1 or an alpha error and a type 2 beta errors. So let's look at our table first and we'll get into some definitions here. So the truth about the population, and this is our conclusions based on our sample. So let's assume the null hypothesis is true, but we reject it anyway. That is a type 1 error. The correct conclusion would be if it's true and we fail to reject. Let's say it's false, and we reject it. That would be ideal. If we reject a false statement, that's true. A type 2 error is if it's false, but we fail to reject. I would definitely mark up these definitions. Important, and we'll see them, we'll use them a lot. So if we reject the null hypothesis, when in reality it's true, that's a type 1 error. If we fail to reject the null hypothesis, when in reality it is false, type 2. So again, they're kind of those opposites of each other. So again, make sure we kind of get used to differentiating between the 2 of those, and we'll do a lot of practice with this. All right, let's try to interpret a type 1 and type 2 errors, both generally speaking and in context of the problem. Here's our scenario. Let's go ahead and take a second here, read through this, and we'll read through it together. Okay, so we have, does the job satisfaction of assembly workers differ when they are expected to work in a self-paced versus a machine-paced environment? So a little typo here. There we go. Data from 50 workers resulted in 60% of workers saying they preferred the machine-paced environment. Conduct a hypothesis test with alpha is equal to 0.05, also known as 5%. Assuming the assumption is that 50% of workers prefer a machine-paced environment. Okay, first things first, we need to figure out, are we dealing with a proportion or are we dealing with a mean? Take a second now and decide which one it is. Okay, so from here, hopefully we've seen that we were given things in terms of a percentage. So again, with proportions, we're either given things in terms of a number of trials and successes, or we could be given a percentage in a sample. So here we have data from 50 workers resulted in 60% saying they preferred the machine-paced. We're not actually going to conduct a hypothesis test right now. We're just going to get a general idea of what it's going to look like. So if we think about here, first thing we have to figure out is what our null hypothesis is. It's what we're saying our assumption is. So we got conduct hypothesis alpha equal to 0.05, assuming the assumption is that 50% of workers prefer this. So since we're dealing with proportion, our null hypothesis comes in terms of p. And the assumption is 50%, so we say p is equal to 0.5. Now, for our alternate hypothesis, so H sub A, it's P, and now we need to figure out what we're looking for. So, we want to see here if workers prefer this machine-paced environment, right? So our sample is giving us a 60%. So if we want to think here, if our sample says 60%, should we be testing greater than, less than, or not, or just different from? Now in this case, it's kind of open-ended. So we're going to use the logic that since our sample is higher, we're going to go ahead and actually test if it's higher. Now a lot of problems will tell you exactly what to conduct, but as always, I like to make our notes more challenging than our practice, as well as our exams. So in this scenario, this would be using your logic to say that, okay, since my sample's at 60% and former data, former parameters are saying 50, I'm going to check to see if it's higher. Now, we're not actually going to do the whole hypothesis test here. We got our null and our alternate, so let's go ahead and write up these errors. So considering a type 1 or alpha error, generally speaking, this is we reject null hypothesis when in reality it is true. For a type 2 error, generally speaking, we fail to reject null hypothesis when in reality it is false. So again, we're just going to keep plugging in those definitions so we get them down pat. So now let's think specific to this problem. So here, we're saying that more than that 50% prefer the machine-paced environment, right? Because there are two possible things. So, okay, do they like self-paced versus machine-paced? So our problem here, our thing is given the assumption that 50% prefer the machine-paced. So we're looking at the null hypothesis as being 50% prefer machine-paced. So if we reject it, here's specific to this problem. So we reject the null hypothesis. So we reject our null hypothesis, right? So we want to think about the wording here. So essentially what we're saying is if we reject that, in reality it's true, we say that there is sufficient evidence to show the true proportion of workers who prefer a machine-paced environment is greater than 50%. So that's taking it from the general to the specific. So we're rejecting it. So we say that there is sufficient evidence to show the true proportion of workers who prefer a machine-paced environment is greater than 50%. When actually, there is not. So we're saying there's sufficient evidence to show this, but in reality, no, it's not. So the null is true in this case. And again, this is one of these things, we're going to have a lot of practice doing this. It's just getting the practice in. All right, let's look at our type 2. So here we fail to reject it. In reality, it's false. So here we say that there is not sufficient evidence to show the true proportion of workers is greater than 50%, when actually it is. So again, key ideas here is what we're trying to say from this. So, my best, trying to make it a little more readable for you guys. So in context here, type 2 errors, we fail to reject the null. So we say there's not sufficient evidence. So that's what it means when we fail to reject. If we reject, we're saying there is sufficient evidence. If we fail to reject, we're saying there's not sufficient evidence. And then we're restating what it is. So the true proportion of workers is greater than 50%, when actually it is. So type 1, reject when we shouldn't. Type 2, we fail to reject when we should. All right, let's take another one of these. So first we know we need our null and our alternate, right? So I'm gonna get these set up. Okay. So here, we have a potato chip producer and its supplier agreed that potato shipments must meet a certain standard. Each time a shipment is delivered, a sample of 1,000 potatoes is taken and they are checked for blemishes. Now, let's say in this scenario, it was found that 120 had those blemishes. If greater than 10% have blemishes, then the entire shipment is rejected. Conduct a hypothesis test with alpha is equal to 0.10. So, right now, what are we dealing with, means or proportions? Hopefully you thought proportions, right? Because we see this is a little more typical of a problem, right? So we're given the number of successes, or the number of blemishes in this case, is 120, and our sample size is 1,000. So we're dealing with a proportion. So our null hypothesis is always equal to. So here, that criteria we're saying is 10%, right? So we're assuming it's 10%. So we're going to go ahead and list that as a decimal. And then our alternate hypothesis here. So in this case, we're saying if it's greater than 10%, it gets rejected. So let's go ahead and set that up as a greater than problem. Okay, so generally speaking again, for type 1, we reject null hypothesis when we shouldn't. So again, I'm cool. I'm going to throw a couple different synonymous ways of saying it in here. Type 2, we fail to reject null hypothesis when we should. So again, both those things mean the exact same thing. All right, let's get specific here. So the null hypothesis is that it's that 10%, right? So we're saying it's okay. So in this case, we reject it. So let me get the exact wording I used over here. So we say there is sufficient evidence. So let's go ahead and use that same wording here just so it's consistent. So we say there is sufficient evidence to show. We're talking about proportions, so the true proportion of, and now in this time we're talking about potatoes with blemishes, so the true proportion of potatoes with blemishes is greater than 10%, when actually it's not. So again, we say there is sufficient evidence to show that the true proportion of potatoes with blemishes is greater than 10%, when actually it's not. So in this scenario, it just so happened that that sample of 1,000 potatoes we took was not really representative of the whole thing. So we rejected that whole shipment. And hopefully in class, we've got a little more detailed discussion, again, of like which one's better, which one's worse, pending the scenario. Again, we'll do a lot of time talking with that, but for as always, the sake of the notes are kind of the review. It's not meant to totally replace that in-class time as always. Now let's take a look here at our type 2. So in this case, we say there is not sufficient evidence to show the true proportion of potatoes with blemishes is greater than 10%, when actually it is. So in this case, right, we grab that sample of 1,000 potatoes. We say, hey, we're all good. We're not above 10%. But actually, all the other potatoes were terrible, right? So we got a bad sample. Maybe, we just happened to pick the ones that looked okay. Okay, so at this point, we should have those down path. And again, we're going to do a lot more practice with this in class. This is just meant to be kind of a rough overview. Okay, now is the time we're actually going to crank through some hypothesis tests. So as we can see here, we're going to do 1, 2 for proportions. We'll talk about some means. Then we'll do 2 with T, 2 with Z. So this is the point where we're going to kind of really go through how to actually do these calculations. So whatever you're using, whether it's GeoGebra or a calculator, go ahead and grab that now. So we got those same scenarios as before with the proportions, where we're dealing with machine paste versus self-paste. Then we'll do the potatoes as well. Okay, so we've already read through this, right? And we knew what our null hypothesis was here. So in this case, we had, it was a proportion, and it said the assumption was equal to 50%. Our alternate, we talked about it being greater than that 50%. So again, notice these numbers are literally always the same, right? So when we typed these up before, same number. Oh, so this was a typo actually. Whew, messed up there. Go on back. So it's always good to check your work, right? So these are always the same number. My bad. I think I was saying 60% there, so I typed it. So again, we always want to make sure. So take a second now, flip back, make sure we correct that. So again, the value in question here in our null and alternate hypothesis is always the exact same number. It's the assumption. This is all that changes. So here they were both 0.10, and here both 0.0 or 50. Okay, now stating our alpha. So here we're told to use 0.05. Now I could give you that as a direct decimal, or I could expect that as a percentage you would turn it back into a decimal. Okay, so this is kind of like the work shown. So this is where we kind of sketch things out. And then now we need to calculate that p-value, right? So let's go ahead now and open up, I said, GeoGebra calculator, and we'll go ahead and calculate a p-value. Calculator people, you guys are going to this screen. So we go to stat, tests, and then we're going to be using these options. So we're either going to use a z-test, a t-test, or a one-prop z-test. So again, calculators, we're looking at 1, 2, and 5 for our buttons here. So 1, 2, or 5. If you are in, well, specific to this one, we're doing with proportion, so let's go ahead to choice 5. And then hang out, GeoGebra. So our view, we're just going to keep that same default view for the semester. So we're going to get a spreadsheet open, we'll get rid of graphics, we'll go ahead and get our probability calculator open. And like I said, I kind of always leave the algebra tile open should I need it. So we're under statistics. All right, so our tests here for this one, we're using z-test of a mean, t-test of a mean, or z-test of a proportion. So oddly enough, this actually lines up well as choice 1, choice 2, or choice 5. So pretty good there. Synonymous with the calculator. So in this case, we're in proportion, so we are here. All right. So let's look at what we need for both these, right? The null hypothesis, right? So here it's listed as p sub 0. Here it says null hypothesis, right? So what we're plugging in there is we're looking at our null hypothesis. The number is 0.50, right? So let's go ahead and plug that in. If you put the 0.50, just default to 0.5, that's fine. Okay. Next thing we need now. In GeoGebra, it has us do our alternate next. Here, it has us do our alternate at the end, which is fine. We're looking for successes and trials, right? So let's go ahead and switch. So we're looking at a greater than hypothesis, so I'm going to go ahead and choose greater than for these. Now again, we need successes and we need trials. So this one's meant to be a little bit more challenging. So let's see. We have 50 workers, and it said 60% of them said they prefer it. So we cannot put 60% in there because it's looking for successes. That's a number. So if we think about it, we need to figure out what 60% of 50 is, because I got 50 trials, or 50 N participants. So to figure that out, I would do 0.6 times 60, and you'll arrive at 30. So my successes would be 30, and my trials would be 50. Over here, successes 30, trials 50. So in the calculator, we're always going to use calculate, not draw. So what we're looking for here is our P. So here it's just not P hat, just P. Here, same thing. We want just P. So we see we get the same number, right? So we got 0.0786, 0.0786. Awesome. Let's go ahead and write that out. So our p-value, 0.0786. Okay, again, the more decimals the better, but usually 3, 4 should get the job done. You can always use more, but don't feel like you need to. Okay, now is where we have to make our conclusion. So on your notes, I actually sketched this out real nice here for you guys on the practice, where it says p-value less than alpha. And I put yes or no for you guys to circle or bold, whichever you want to do. Again, you don't technically need to write that up in a formal hypothesis test, but for our purposes, while we're getting used to just getting that conclusion down path, it helps. So what I'm asking you is this number less than this number? take a moment now, pause the video, and answer that question. So again, hopefully we've learned our strategies by this point for working with decimals, moving them over, to arrive at the correct conclusion of this is false. So the p-value is not less than alpha. So in that case, if we think back here, where were we? Aha. So if it's less than alpha, we reject the null hypothesis. If it's not, we fail to reject. So in this case, we said it is not less than alpha. So our first part here is we're going to write since. So we're going to say since the p-value of, so this is where we write up our conclusion, so 0.0786 is not less than 0.05, we fail to reject the null hypothesis. So just like with confidence intervals, we're looking for a two-part thing here. So this is the statement, right? We either say since the p-value is less than alpha, we reject the null hypothesis, or in this case, we would say since the p-value is not less than alpha, we fail to reject the null hypothesis. Now for our conclusion, right? Thus, we do not have sufficient evidence to say the true value of the population proportion. And then we're talking about workers who prefer the machine-paced environment, right? So the true proportion are, we don't have sufficient evidence to say the true value of the population proportion of workers who prefer a machine-paced environment is, so context here, right? So let's look at this, break this down. Sentence one, since the p-value of the p-value is not less than alpha, we fail to reject the null hypothesis. So we either reject or fail to reject. The next one, so procedurally here, since we failed to reject, we want to put that in words. Thus, we do not have sufficient evidence to say the true value of the population proportion. So that's kind of cookie cutter, right? I would change this word to mean if we were dealing with means, right? And then we're talking about context. So of workers who prefer a machine-paced environment is, and at this point we're going to restate that alternate. So is greater than 0.50. I know that seems long. It's probably because the text I'm using right now is in all caps and fairly large. But again, it's two sentences. We're going to get through a couple of these. We'll have them down pat. So pause the video at this time if you're still working. Otherwise, I'm going to go ahead and move on. So in this one, again, we're looking for a null hypothesis here. So we're saying if it's greater than 10%, less than 10%, right? So 10% is the cutoff, as we already talked about. And we're doing proportion, so it's equal to 0.10. And then here we're looking at a greater than again. So greater than that 0.10. The alpha they tell us to use here is 0.10. And again, in class, we've done a lot more discussion about the different levels of alpha, why we choose them, how we choose them, when we choose them. And again, the rationale behind that. So again, if you weren't in class, you will have missed out on that. Again, this is meant to just be supplementary, like a review, right? Okay, so we got our information here. Let's go ahead and run our test. So in the calculator, we're dealing with a proportion again. So now it's 0.1. Now we need our successes and our trials. Right? So I'm going to go ahead and change. It's still greater than. We're good there. So it says we have 1,000 potatoes and 120 have blemishes. So I'm going to go ahead and do 120 and 1,000. Go ahead and calculate. For GeoGebra, so let's change what we have here. So 0.1 greater than, we had 120, and then 1,000. So quick check. Got the exact same P for both, so 0.175. So 0.175. So again, I'm just typing down that P value. So now it's conclusion time, right? we're looking at our p-value. Is that less than alpha? Hopefully we said yes, right? So in this case, yes, it is. So for our first part of the conclusion, since the p-value of 0.0175 is less than our alpha 0.10, we reject the null hypothesis. So that's our sentence one, right? So there's exactly two ways we can write sentence one. The last one we've seen here. So since the p-value of this is not less than this, we fail to reject. In this scenario, we said since the p-value of is less than this, we reject the null hypothesis. And now our conclusion is going to be very similar, right? So thus, we have sufficient evidence to say the true value of the population. Here we're still dealing with a proportion, right? Proportion of, we're talking about potatoes with blemishes, is, and our alternate here is greater than, so is greater than, you could say 0.10 or 10%. And there we go. That's it. That's our conclusion. All right, so take a minute now if you need to pause and catch up. Otherwise, moving on. Let's get into our means here. We have with sigma known versus sigma unknown. So sigma known, that's our z, right? This is our z work here. My bad, this says intervals. This should say tests. And then same thing here, tests, my bad. I was typing up these notes during our confidence intervals unit, so. Okay, so just as always, right, we're gonna be directly told what sigma is. We're seeing the phrasing population standard deviation. We're working with z-tests. Maybe we need to calculate the sample mean if we're not given it, but oftentimes it's given. Sigma unknown. You're not given a sigma, right? So we've kind of got that down path after the semester of working with these. But again, I just want to let you know it stays the same. You're going to either utilize an S, S sub X, S sub P, depending on the textbook, the phrasing, et cetera, to signify it's a sample standard deviation. So again, the wording here would be sample standard deviation. So let's use, let's go ahead and throw that in here. So sample standard deviation. Again, occasionally we might have to calculate it from that raw data as well, working with t-tests. And as always, we still may need to calculate the sample mean if we're not told, right? Okay, 4 more examples to go. Okay, so if we're looking at this problem now, again, the title is meant so that you know, but let's read through it and see how we know. So we have sunspots have been observed for many centuries, and records of their occurrences go back thousands of years. Can you tell this one's from a textbook? Yes, and it's also really true. That's interesting stuff. So a random sample of 20 periods of time from the colonial era resulted in the following data related to occurrences of sunspots in a given fixed interval. Data. Not going to read that to you. Okay. Previous studies indicated that sigma is equal to 35 and the mean number of sunspots to be mu is equal to 43. Do the data indicate the mean sunspot activity was lower than 43? So here it's very, very obvious we're dealing with means, right? First off, we're given a list of data. You're never given a list of data when we're dealing with proportions, right? Unless it's like, okay, I take that back. So some of those ones we did last unit, it was like, here's a sample of 10, how many fit the criteria, right? But in this case, right, we're seeing here that we're given a list of quantitative information. It's not a success or fail type problem. They're not saying how many of these are greater than 50, right? So we're given our mean, and then we have sigma. So we're dealing with a z-test here. So for this one, you could just use M if you want, or if you want to get the cool proper symbol, do /mu and hit space, and that'll give you mu. So our null is always equal. So here we're saying we know from these previous studies that mu is 43, and we're testing if the data can indicate that it was lower. So I'm looking as mu less than 43. In this case here, let's see, did I give you an alpha? No, I did not. So let me throw one in here. It'll be here when I actually print out these notes for you. Say use. Let's just go with that. Okay. So let's use our alpha there, 0.10. And again, when I print the notes for you, that'll be there already. Okay, so now we define our p-value, right? So we determine because we have sigma, because we have a mean, we're dealing with a z-test. So calculator, first one, z-test. Again, we see we have the data versus stats option here. In GeoGebra, let's go ahead and use a z-test of mean. Okay, so if we're looking at this problem, right, we're given enough data here. So a couple of things. I'm going to go with the formal way of typing in the calculator. But we know as always we could just go ahead, since we're dealing with z's anyway, we could just calculate a sample mean by adding and dividing by how many there are. But I'm just going to go ahead and use the calculator for it. So before we do our data, we can switch it over to data if we want. We got to put that data in. So let's go to stat, edit. I'm going to clear this by hitting clear and enter. And then I'm just going to move over here so I can actually see. So typing in my data, 12.5. I'm going to go ahead and pause the video at this time as we know I'm just typing in the data. Okay, so if we're in the calculator, go ahead and make that bigger. I'm not gonna lie, I typed in the other data set too, so we'll get to that one later on. But again, I just typed everything in L1 for this first one. So to execute the test in here, we're in z-test. We chose data. Our null hypothesis here is 43. The sigma they gave us was 35. We happen to type this problem into list 1, so we're going to leave it there. Frequency, we always leave at 1. And then here we're using a less than. So go ahead, take a moment, hit calculate once you have that. All right, so our p-value here, we got 0.90, and if we round it to say 3, so 0.905. So that's our p-value there. Let's go ahead and repeat that in GeoGebra. So if you're using GeoGebra, hopefully you type this into column A here. My column B is for a different problem that we'll get to later on, but if not, go ahead and pause the video. Otherwise, let's go ahead and get some of our data here. So our null hypothesis here, we were saying it was 43. That's the same as the other one, right? We're looking at a less than. Now our sigma we were told was 35. Our sample size here, n, if we look back, we were told 20, and again we have 20 pieces of data, so I can see that here with 20. So let's go ahead and adjust our sample there to 20. Then lastly, to get our mean, I would just highlight column A, do this, one variable analysis, show statistics, and we see our mean is 53.25. So 53.25 is our mean. All right, I'm gonna drag it over a bit. Okay, and again, we got our P here, so it's 0.905. Which again, if we round it, same thing, right? So the other one, it looks like it showed 4 decimals, so we could round and get 0.049. Either way, it's a huge p-value. It's really close to 1. Okay, so let's go ahead and look at our conclusion here. So I'm saying, is my p-value less than alpha? So is 0.905 less than 0.1? Not even close, right? So in this case, since the p-value of 0.905 is not less than our alpha, so 0.10, we fail, just here with a comma, we fail to reject the null hypothesis. So again, it's a false statement, it's not less than alpha. So we say since p-value is not less than this, we fail to reject the null hypothesis. Thus, we do not have sufficient evidence to say the true value of the population. So this one's a mean, so we could say mean or average. We say number of sunspots, so mean number of sunspots is, we're looking at less than, so less than 43. All right, let's do another one here. So, do another one with Z's here, right? So we have a random sample of 46 adult coyotes from Minnesota is taken. It's found that the sample mean is 2.05 years, and the population standard deviation is known to be 0.85. So again, population standard deviation, that is sigma. Formerly, it was believed that the mean was 1.75. Do the sample data indicate that coyotes in this region of Minnesota, I should say tend, not tend to live, tend to live longer than the average of 1.75 years? Use alpha is equal to 0.01. Okay, let's go ahead and crank this out. So we're dealing with means, so we got mu. And our assumption here is that 1.75, so I'm going to go ahead and type that. Here we're saying, do they live longer? So that's a synonymous way of saying it's greater than 1.75. And we're told alpha is 0.01. Okay, so if I was using GeoGebra, I could just go ahead and adjust accordingly here, right? So if I was using a calculator, I would be doing a z-test again, and this time we have stats. So our sample mean we had was 1.75, and we're looking at greater than. So let's go to 1.75. I'm going to go ahead and switch this down here to a greater than test. Over here, let's go 1.75, looking at greater than. All right, so we know that our sample mean was 2.05 and our sigma was 0.85, and we had 46 adult coyotes. So let's go ahead and switch up some stuff here. So sigma 0.85, sample mean 2.05, and we had 46 for our sample. Let's go ahead and recreate that in GeoGebra as well. So our mean 2.05, sigma 2.05. Oh boy, an issue here. There we go. Play around a little bit to get that to work. 0.85, sample 46. So again, 2.05, 0.85, 46, good. Let's go ahead and calculate. So we got our p-value of 0.0083. So p-value 0.0083. So we're looking, is that less than alpha? I hope we all answered yes. And again, multiply, write a number line, do what you need to do, but we got to be able to make these conclusions correctly. So since it's a true statement, so we have since the p-value of 0.0083 is less than, we reject the null hypothesis. So since it's less than, we reject. Thus, we have sufficient evidence to say the true value of the population mean life expectancy for these coyotes is, we're looking at greater than, so greater than 1.75. So essentially we're saying, statistically speaking, these coyotes live longer than the others. They live longer than the average. All right, take a moment, pause if you need to, otherwise we're moving on. Okay, so here's going to be our last two examples. We're going to deal with those t-tests, right? So let's go and check them out. So in this case, we are given, we don't know it, but again, you won't have that title on every question, sadly. So we have a certain drug for hair loss is undergoing clinical testing with a sample of 21 patients. The following data represents the number of days before hair regrowth was noticeable. Data. The former drug utilized had a mean time of mu is equal to 12.5 days. I should say days. Do the data indicate the new drug is different from the old drug? Use alpha is equal to 0.01. So, why this is T and not Z? I don't have sigma. I don't see the words population standard deviation, and I surely don't see the sigma symbol in here. Thus, it is a t-test. So, if you're using a calculator, we know we need to enter this in, so let's go to stat. Edit. As usual, you could clear your L1 for the sake of the video and its time. I just typed the data in L2. And I checked, going all the way down. So my 21 is the length of my entry, so I know I got all the data there. If you're in GeoGebra, you could type it in column A, or as I mentioned earlier, I just went ahead and typed this in column B to make the video a little bit shorter. So pause if you need to at this time. Using GeoGebra, using a calculator, go ahead and enter in that data set. So let's go ahead and get some things set up here. So for our null hypothesis, if we're looking at our problem, we know we're dealing with means. So let's go ahead and type in mu equal to. And here it's saying that this former drug had a mean of 12.5. And now for our alternate, here it says, do the data indicate the is different from. So it could say is different from, is not equal to, right? They mean the same thing. If you want to get fancy, you could put not equal here. Is it not equal? But the nicer way to do this, if you're typing, is to do /NEQ. So misspell the word neck, right? So /NEQ gets you the fancy symbol. So again, just that, hit space, and we're good to go. So not equal to 12.5. The alpha they tell us to use is 0.01. Let's go ahead and get our p-value, right? So if I'm in GeoGebra, I need t-test of a mean. Here we're looking at 12.5. We wanted a not equal to, so not equal to. And now we don't have any of this data, right? So we don't have a sample mean. So we need to find it. So in GeoGebra, I would go ahead and highlight. So click over in one of these. So a lot of you guys have had this problem where you'll click and be like, oh, it's not showing up. The way to alleviate that is the first thing you need to do is click in an empty cell. So if I'm over here, I click and I say, oh, it's not showing up. Just click in an empty cell and then it shows up. So I want to use column B. Again, you might be using column A. We know by this point that that doesn't matter, right? This is just where I happen to have my data. And I'm good to go. So my mean here is 170952. So I'm going to go ahead and type that whole thing in. And sometimes you got to play around a bit with GeoGebra. Just the way it works. It's a free program. And then S. So our sample standard deviation, I have 9.9995. And then our N, so our sample size, again, they listed off here, so I can see it's at 21, or I can see here 21, or in the problem it said 21. Boom. In the calculator, so I used L2, and again, you may have used L1, totally cool either way. But let's go stat, test, I want a t-test. We have data. So my mean here, 12.5. Now for me, like I said, if your data is in list 1, leave it as list 1. But just a review of how to change it if you so choose to, like I did. I'm going to go ahead and clear this. Go list, and I want list 2. Leave frequency at 1. We want it not equal to, and then calculate. All right, so our p-value, let's see, over here we got 0.048. Up here I got 0.048. Wonderful, we typed everything in right. So my p-value, make sure I have the right number, 0.48, yes. All right, let's do our conclusion, right? So we have since the p-value of 0.048, now, is that less than 0.01? Hopefully you said no. Is not less than 0.01. We fail to reject the null hypothesis. Thus, we do not have sufficient evidence to say the true value of the population mean. We're talking about days. Let's see, days before hair regrowth was noticeable. Right, so context of the question is, and we're just talking about not equal to, so we could say is not equal to, but usually for colloquial reasons, right, so saying is different from sounds better. So we can't say is different from, 12.5. Done, right? So it was not less than, so we failed to reject. Thus, we do not have sufficient to say the true value of the population mean days before hair regrowth was noticeable is different from 12.5. All right, on to the last one, so pause if you need to. Okay, so related to agriculture. Groundwater, unfortunately. Oh, wow, that was weird. This should be like a title here. My bad. As you can tell, this one's definitely from a textbook, so like pretend this isn't here. That's like the title. So I should start reading here to make this sound better. Unfortunately, arsenic occurs naturally in some groundwater. Gives us the reference, right? A mean arsenic level of mu is equal to 8.0 parts per billion. It's considered safe for agricultural use. A well in Texas is used to water cotton crops. This well is tested on a regular basis for arsenic. A random sample of 37 tests gave a sample mean of 7.2 with the sample standard deviation of 1.9. Does this information indicate that the mean level of arsenic in the well is less than 8? Use alpha of 0.01. So I see an S, right? So that means I'm dealing with a T. I'm dealing with a T test, right? So let's say our null hypothesis we know what it means. So we got mu equals, we're told it's 8.0, right? So that's what we're saying our null is. And we're looking at less than 8.0. So mu less than 8.0. Alpha we're told to use is 0.01. So this would be the same as being 99% confident, right? All right. And then we need our p-value. So we have our test set up here. We have just some stats given to us. So if I'm in a calculator, I would go to stat, t-test, and then click over on stats. So we got 8. Our sample mean here we were told is 7.2. Sample standard deviation was 1.9. It said 37 tests, so that's our sample size, and then we want less than. For GeoGebra, so we got 8, 7.2, 1.9, so 8 less than 7.2, 1.9, then 37, let's make sure it's right. So null hypothesis was 8, 7.2, we're looking at 8 less than 1.937, good. Just hit enter there, got our P. Let's see if we get the same one in the calculator. We did, 0.0074, if we round here. Okay. All right. Just did a drum roll on my desk if you didn't hear that. Is that less than 0.01? Yes, it is. So we have, since the p-value, oh, I spelled that totally wrong. P-value of 0.0074 is less than 0.01, we reject the null hypothesis. Thus, we have sufficient evidence to say, so again, we reject it, so we do have sufficient evidence. Thus, we have sufficient evidence to say the true value of the population mean arsenic level for this well. So it's context, right? And then we're looking at the alternate here. So is less than 0.0. So basically what we're saying is that well is good to go. We can use it. We're safe. We're 99% confident, right? Because that's how that alpha works. So again, 0.01 is the same thing as being 99% confident. So we are good to go. All right. With that, that is the conclusion of these notes. Again, these are not all encompassing, but if you know everything in here, you're probably good for like an 85% on the test. Hopefully we've gained a lot more from the in-class discussion, but again, your crash course for Unit 7, probability and statistics, is good to go.